run this. Okay, so here my blue is my right. Okay, so my blue is the numerical solution that satisfies the derivative is equal to 1 at the left and u equal to 0 on the right. So the red one is just something I constructed to match the derivative on the left, but I didn't try to match the solution value on the right. So it looks like I think I need to subtract by 0.5 to make it work. Let's do that. All right, now we have our analytical and numerical solutions. They also match pretty well, right? Okay, any questions on the other type of boundary conditions we are enforcing here? All right, if you're interested, there is yet another type of boundary condition we can set, but like that's it's basically a mixture, a linear combination of values and the derivatives. Is called a mixed boundary condition. And the way to derive this is actually very similar to how we derive the Newman boundary condition. It's also going to modify how the weak form looks, right? But like we are not going to go deep into that. If you're interested, there are some references I can provide. What I want to discuss more today is how do we compute the kind of integrals we want to compute in finite elements. For example, we have skipped over how do we compute the integral of phi times f dx because we have been focusing on the case when f equal to 1. In general, f is not equal to 1, right? For example, if my f of x is equal to x squared, right? I mean, that's a perfectly valid function to use. Or f of x equal to, how about sine of, let's say, 2 pi x, right? I mean, this is actually a case we know an analytical solution for. How would that work? How do you compute that kind of integrals? Well, it turns out there is actually a very powerful and very useful way to compute integrals numerically. It's called a Gauss quadrature. The idea is that we know that if f is a smooth function, right, then we know that phi is usually also a smooth function if you restrict phi to one element at a time. So we know that phi f is very smooth within each element. In our case, phi is actually a linear function within any element and within any particular element, and f we assume is smooth overall. So phi times f is smooth within every element. Gauss quadrature is an amazing way to approximate the integral of smooth functions. In that, if you integrate between any, let's say, x j to xj plus 1 of, let's say, any function. Let me just call it a g. Okay. The Gauss quadrature essentially approximates that as a summation of a bunch of quadrature points, usually called k. K goes from 1 to, let's say, m. Okay, that's the number of quadrature points. The value of g, okay, at the location of the quadrature points. So let me just call it c, k, and the ck is basically spaced between -1 and 1, but we are going to be basically linearly scaling ck so that it is going to fill the interval between xj and xj plus 1. which means we are going to be multiplying this with the half width of the integral domain, and then shift it to the center of this integral domain. Okay, so this is the half width, and this is the center of the domain between xj and xj plus 1. So we are essentially evaluating the function g only at a finite set at m discrete points. And we are going to be multiplying this with a wk. And the wk is also going to be scaled to the width of the domain. So I'm actually running out of space here, but wk is going to be multiplied by xj plus 1 minus xj. All right. Okay, so this looks complicated, but like it's actually pretty simple. It's saying that instead of having to integrate, let's say this is my function g, okay? Instead of having to integrate, which is basically calculating the area below this function, which requires the value of the function at every x. I'm just approximating that with a few points. So let's say I'm approximating that with just a few points, each point associated with a different weight, right? So for example, that's it, right? So each point I have a weight really multiplied by a delta function. That's like one of the more mathematical ways of saying that. And each delta function has a different weight, which is wk times the width. Okay, the value of g at these particular points are going to be multiplied with the particular weights and added together to approximate that integral.